Okay, so last time, long before your midterm, we were talking about how to compute settlements, and we talked about modulus-based methods, and now we're going to talk about methods based on the E log P curve. So these are the learning objectives for this block. First part of which is definition, be able to confine the preconsolidation stress. I have all these notation done for the notation that I'm used to, and Holtzman-Kovacs uses a slightly different one. So they use sigma prime P for the preconsolidation stress, and I'm used to using sigma prime C. So I will confess to not have completely converted to Holtzman-Kovacs, and I probably won't because I have to do another class in the other one. So since you're the big adults in this program, I'm hoping that you can figure out my notation versus Holtzman-Kovacs. And where it's really weird, I'll tell you about it, but I don't think it'll be a big problem. And some of this material we're going to build off of the stress strain stuff we already talked about. So we're going to discuss what happens when you take a sample out of the field and why you see a preconsolidation stress even when there's no preconsolidation in the field. And then talk about overconsolidation, what it means, what the sources are, and how it's characterized. There's two main ways of characterizing overconsolidation. And we'll talk a little bit about this reconstructing the curves and some of my opinions about reconstructed field curves. And then finally, the thing that you really need to be able to do is to be able to calculate the magnitude of settlement using the E log P method. And that's your task your first task for the project is to actually calculate the settlement that you're going to expect out there. Which actually you're free to calculate it either with the E log P method or the modulus-based method, whichever one you think is most appropriate for the data that you have. And we'll talk a little bit about how you can estimate compressibilities even if you don't have data for them. So it's helpful to start this discussion with just what is going on in consolidation. The simplest way to look at that is an odometer test, which we're all familiar with. So this is our odometer, and this particular one happens to be a floating ring odometer, which means it has drainage. A floating ring odometer has drainage on both the top and the bottom, and this distance, the height of the sample, is 2 times the HDR is the notation I use for the drainage distance. So because it's draining on top and the bottom, the drainage distance is half the thickness of the sample. So normally we put a load on the top of this. That load is going to apply some delta sigma to the sample, and it's going to sit there and it's going to consolidate. Pretty straightforward. The other type of consolidometer we have is called a fixed ring consolidometer. The big difference between a fixed ring consolidometer and the floating ring consolidometer is this is a single drainage. All the drainage is out the top. You have a stone at the bottom, but the stone at the bottom is sealed off. Notice that I didn't draw the mechanics of this happening, but your confining ring is sealed to the bottom, so all the flow of water goes out the top. And so in this case, the entire height of the sample is HDR, is the drainage distance for the sample. See if I can write that again in a legible manner. This is HDR. The advantage of this method is that you can actually measure the pore pressures at the bottom of it. You can either measure them with a transducer, or you can measure them with a little standpipe. I just said all the flow goes out the top, but if you got a standpipe, some of the flow goes out the standpipe, but you can make the diameter that smaller if it's not significant. But most of this is done by putting a transducer at the bottom these days. In this case, when I apply my stress, notice that immediately what happens is the pore pressure goes up. And how much does the pore pressure go up? Well, it has to go up. If I put the load on immediately, there's no consolidation. So there's no change in void ratio. If there's no change in void ratio, the soil skeleton can't have taken on any more load, because in order for the soil skeleton to take on load, there has to be deformation. So my spring hasn't compressed. So immediately, the change in pore pressure at the bottom is going to be equal to delta sigma z, or the height of the rise in my piezometer is going to be delta sigma z divided by gamma water, it's the head. And then what happens over time? Yeah, so the sample is going to settle, but it's only going to settle because the pore pressure is decreasing, right? And so what's happening here is I'm transferring stress from the pore pressure to the soil skeleton, and that's why the soil skeleton compresses. So that's the basic consolidation test. So we've talked about this already, that I can plot these data either in terms of in either arithmetic space or in semi-log space. And no matter how I plot these, no matter what the field conditions are, I'm always going to see some strain softening behavior early in the sample, almost always. So normally I see, we're going to get some laboratory curve that looks like this. It's got some curvature to it. We make that bilinear. We just fit lines to the two pieces of it, and we call the slope of the upper curve the recompression index. We call the slope of the lower curve the compression index. That's in the case where we're plotting the log of sigma versus the void ratio. And that place where they intersect is the preconsolidation stress. This is just a mathematical exercise at this point. This doesn't say anything about what's going to happen in the field. We're just fitting two lines in semi-log space. It's really important to understand that. And we'll talk about whether there's any physical significance to that in a minute. If I plot them in strain space, which is much easier to do because that's what you actually measure in the lab, then you end up with the same bilinear curve, except the slopes are slightly different. Holson-Kovacs calls this C sub r epsilon for the modified recompression index. It's just equal to C sub r over 1 plus E naught. We already talked about how you get that value. And then you have the modified compression index. And there's no real reason to plot it in log space, by the way, because in the end, in your equations, you need C sub C over 1 plus E naught in the equation. So why, and when you measure it, you're going to measure displacement in the lab, and you can calculate strain. To calculate void ratio is actually hard, and then when you go into the equation, you got to divide by the void ratio anyway. So why anybody ever uses the plot on the left, I have no idea. And then we're going to calculate the settlement using this equation. And there are actually 3 equations. Holson-Kovacs actually give you like 4 or 5. I like to just think of it in terms of one equation. It's easier for me to remember. So it's either C sub r over 1 plus E naught times this change, or C sub r epsilon. Those are equivalent. But the way that I think it's easiest to think about this is just mathematically, there's 3 different things that can be happening, right? I can either start off with sigma prime 0, essentially equal to sigma prime c, in which case all the loading is going to occur on which of those 2 lines? Right. It's called on a compression curve. Delta sigma z is here, and all the loading is going to occur on this curve. Well, what does this equation become in that case? Well, there isn't going to be any recompression, so that part's going to drop out. And I'm going to be loading from really sigma prime 0 to sigma prime final. I wouldn't want to do the calculation from sigma prime c to sigma prime final because there might be a little bit of difference that might just be an error in the way I calculated sigma prime c. And in those cases, we call that situation what? What kind of soil is that? If overloading is on that virgin curve, it's not overconsolidated, it's normally consolidated, right? So this is normally consolidated. Now, what are the other 2 things that could happen? I'll draw the other 2 things on this curve. Well, if the other 2 things that can happen can be associated with, I have a sigma prime 0 that's less than sigma prime c, the preconsolidation stress, right? In that case, what are the 2 things that can happen? Well, if I have a relatively small change in stress, right? If I have a relatively small delta sigma z, this is going to be sigma prime final, and I'm loading only on the recompression curve, right? Well, in that case, this term goes away, and this is I'm going to be loading from sigma prime 0, not to sigma prime c, but to sigma prime final, right? And what's the third thing that can happen? So the third thing is I start here at sigma prime 0, but I have a much bigger delta sigma z, right? And my final, sigma prime final is out here, Now I have to load from here to here. I have to load from point A to B, and then from B to C. And now I'm going to have this whole equation just as it's written here. That at first I'm going to load on the recompression curve, I'm going to load from sigma prime 0 to sigma prime C. That's from A to B, right? And then I'm going to load on the inversion curve from sigma prime C. And I now have to get rid of this thing, from sigma prime C to sigma prime final. And this shouldn't be news to anybody, right? This is all review. Okay, cool. So you can memorize 3 equations, and then for those of you that studied here or used our textbook, you know, we have this, there's OC type 1 and OC type 2, and I don't like any of that stuff. I like to just say, there's one equation, you just have to figure out what the, you know, where you're loading from and throw out the parts that you don't need. So, but if you want to memorize 3, go right ahead. Okay, so let's talk about this preconsolidation stress. In the laboratory, we're almost always going to have a preconsolidation stress. Why are we always going to have a preconsolidation stress? Because we're always going to unload the soil. When we take it out of the field, even if we could get if we could go get a block sample, and we're going to trim our sample out of the block, so there's like almost no soil disturbance, there's still one thing we have changed about the soil. I go to the field, I said I wouldn't do this, but anyway, I go to the field, I pull the sample out, I bring it to the lab. Even if I could do that perfectly, what have I changed? Took it out of the ground, I changed the state of stress. It's basically I unloaded it. So even for soil, and we know from looking at stress strain curves in soils that they're hysteretic, that they usually unload at stiffer curve than they were loaded on. So we almost always got plastic deformation, and they're going to load it more stiffly. So this is what's going on. Here I am in the field. There's my little sample in the field that I'm going to take. I'm going to take that sample. I'm going to take it out. And I'm going to take it to the lab and test it. So it's always going to look like this because I've unloaded it. The question is this sigma prime C I saw in the lab actually representative of what's going on in the field? It may be or it may not be. How are we going to know whether or not there's actually a preconsolidation stress in the field? Well, we're going to calculate sigma prime, so it may not be representative. We're going to calculate sigma prime Z in the field. Right? And if that value is over here, then I'm going to see loading on the recompression curve. If that value is in some region very close to here, if it's right here, then it's normally consolidated. Could that value actually be out here to the right of sigma prime C? It can be. We call that underconsolidated. That would happen, for instance, if you were out to some site that had been, that you went to a site, you didn't know this, but had been preloaded, and it was under consolidation, but all the excess pore pressure hadn't dissipated. And then you went and sampled it, then it's actually be underconsolidated because current effective stress state is actually going to be, you're actually going to measure preconsolidation stress in the lab, and it's actually, it's there in the field, but you're actually beyond it at the moment because of the it's in the middle of being consolidated. That's kind of a weird thing. It doesn't happen very often. So if sigma prime C is approximately equal to sigma prime 0, it's normally consolidated. If it's substantially less, it's overconsolidated. And if it's greater than, it's underconsolidated. And there's a little discussion of underconsolidation in your text. So that basically, the other place that can happen is if you've got artesian conditions. If anything that you've got elevated pore pressures that are going to make your effective stress in the field actually lower than you would calculate from a static standpoint. Because you're going to calculate sigma prime 0 based on statics, right? You're not going to measure excess pore pressure in the field. You're going to assume it's a static condition. Well, if it's not a static condition, then what the issue is really that the sigma prime 0 that you're calculating in the field is wrong. the one that you're calculating at home is wrong. And if you actually measured the pore pressure, you calculate the right one, you'd find out it's normally consolidated. But that does happen. All right. Let's talk about sample disturbance. Now, besides unloading the sample, what else happens when we sample in the field? Well, we usually disturb the structure of the soil some, and it depends on how high quality our sample is. The The best sample we can get is to get a block sample and then bring it to the lab and then trim out a little sample out of the middle of the block sample. And that happens, but not very often. And the next best thing we can do is get a fairly large Shelby tube and then trim the sample down so that the specimen that we're going to use in the lab is actually a smaller diameter than what we originally sampled. And the third thing we can do, which we do a lot, is we just go out there and get a sample and we extract the sample right out of the tube and then we just use it the way it is because it's easy and it's fast. And that's going to give us the most disturbed samples. And then within that practice, the smaller diameter of the sample, the more disturbed it's going to be. So as we see curves that get more, that move in this direction, they get soft. Two things happen. They get softer, and the preconsolidation stress gets less and less distinctive. That's an indication of a sample that's been disturbed. So as the soil gets more and more disturbance, locating sigma prime C it gets harder and harder. Well, that's a problem. And we're going to talk about, so that leads to this desire to somehow then correct the curves, which I'll talk about in just a minute about how we do that. And there's a whole section of the book about reconstructing curves, and there's a lot of stuff that's problematic with that. But I think it's important to talk about what can generate this preconsolidation stress, because our normal concept of the preconsolidation stress, and this is a table right out of your text, is that, well, the soil's been loaded and unloaded. Well, that's one way that you can get a preconsolidation stress, and that's this first block here where you're basically removing overburden somehow. Either it was geologically removed, in other words, there was erosion that unloaded it, or in the case of glaciation, you had glaciers that were around for a long time and they retreated, or it could be a man-made one. It could have been an embankment was there, some structure was built and then removed. And that's the one we think about the most, and that certainly is a form of getting preconsolidation. But there's really other ways that you can get preconsolidation stress. In fact, most people will tell you that even soil deposits that are geologically normally consolidated will have a relatively small preconsolidation stress, because the soils develop structure after a long period of time, even if they don't undergo an additional load. But there are other sources. If we have changes in pore water pressure, that's the same as well. If you go and pump and you lower the regional groundwater table, the total stresses don't change too much, but you're decreasing the pore pressure. So what happens to the effective stress? It goes up, and you're going to have preconsolidation even though there was no total stress change. Because remember, it's a change in effective stress that causes consolidation. So that's a very common method for that doing. And if you have artesian conditions, it can actually be in the opposite direction. So pumping anything that changes the effective stress. Soil aging, this is the one I was just discussing, is even for normally consolidated soil, it's going to undergo creep and secondary settlement after it's deposited. It's going to, another way to think about it, it's going to develop its own structure, and that's going to generate some stiffness that once you overcome that structure, it's going to be softer. So even normally consolidated soils normally have a small preconsolidation stress. If you change the pore chemistry, you can change the way the soil wants to be. We discussed that. In fact, you saw the quick clay videos, right? I posted those. I did, right? Yeah. You know, that's a good example of that. What's really happened there is there's been a change in the chemistry of the soil over geologic time. It used to be all those soils were deposited in salt water, and now they're not. And so they have a stiffness that as soon as you overload it, it's gone. In fact, dramatically gone. But those soils aren't necessarily overconsolidated from a stress standpoint. They're overconsolidated from a structural standpoint and basically from a chemistry standpoint. And then precipitation or cementing agents. There is some evidence that even in clay soils and certainly in sandy soils, it's possible to get cementation actions, which is going to give your soil a stiffness that is going to go away once you exceed the capacity of that particular stiffness that's been created. So it's not all just loading and unloading. So how can we characterize the overconsolidation? There's two ways to do it. The most common one by far is by the overconsolidation ratio, which is just the ratio of the the preconsolidation stress divided by the current vertical effective stress. This is the original way it was created and the way it was most defined. The other way to do it is the overconsolidation margin, which is a creation by Professor Caduto. And I'll explain to you in a minute why this might make sense. These both work. You can use either one. There's some rationale for using one over the other, but you'll most often find the overconsolidation ratio used in literature, but there's definitely an advantage to the margin, and that's what I'm going to explain right now. So if I'm thinking about what's going on in the soil down here, and there's some change in stress, right? We have erosion that's going to cause a change in effective stress. In fact, it's going to cause a negative change in effective stress, right? It's going to reduce the total stress, which will eventually reduce the effective stress. Whoops. So if I'm thinking about this point right here in the soil versus this point, so point A, B, and C. So if this is my preconsolidation stress for point A, where is, if I took delta sigma z off, where's my current vertical effective stress in relationship to the preconsolidation stress for point A? Well, it's back here a distance delta sigma z, right? And it's right there. Now, point B is going to be deeper, so this might represent what was going on at point B because it's going to have started at a greater effective stress. So this might be the preconsolidation. This would be for point A. This would be sigma prime C for point B, and it also was unloaded the same amount, right? So delta sigma z. And similarly for point C, this might be the preconsolidation stress for point C. And if it was unloaded, it was unloaded the same amount, delta sigma z. Now, will those three elements have the same overconsolidation ratio? Well, the numerator is going to be the same for every one of them. Oh no, that's not going to be the same. Sorry. The numerator is not going to be the same for everyone. But the change in effective stress on the bottom is going to be the same for everyone. But they're not going to have the same overconsolidation ratio because this distance, if you want to think about it, are the same, but one's starting out at a higher stress. So the rationale for using the overconsolidation margin is if the source of overconsolidation is unloading, everybody was unloaded by the same delta sigma, so that they should have the same overconsolidation margin, but not the same overconsolidation ratio. And that's the rationale. If the overconsolidation occurred because of some cementation action or something else, that might not be true. But you can use either one of these. And normally, we're dealing with soils that are either highly overconsolidated or normally consolidated, and it really doesn't matter which one you do as long as you stay on the recompression curve. But if you're dealing with a soil that's going to cross the recompression curve, then you really ought to figure out which one of these methods gives you the most accurate answer and use that one. Because there's no reason, if the source of preconsolidation is just a fixed stress that was unloaded, then the reconciliation margin, the overconsolidation margin makes more sense than the overconsolidation ratio. That's the rationale anyway, but either one's acceptable. Okay, let's talk about how to find the preconsolidation stress, because that's pretty important if we can't figure out where these two lines intersect. So I think most of you, has everybody here done Casagrande's construction here to find the preconsolidation stress, yeah? Anybody who has not? Then you need to read up on it. Nobody's fessing up to nothing having done this. So we know this method. We find the place in here where there's the greatest curvature. We draw a horizontal line. We draw a line tangent there. We bisect that line, put it in there. We take this line. We draw a line up there where they intersect to come up here, and there's the preconsolidation stress. And if your laboratory curve looked like that, do you need to go through that process? If you actually had this laboratory curve, how would you find the preconsolidation stress? Well, personally, I'd walk in there and say, it looks like it's about right there. Curve turns over there, that's it. Now, what if this, I'm going to use this one example. What if this was your laboratory stress term? Where's the, you say, well, this is the peak area, and I'm going to draw this line. There's a tangent. I'm going to split those this way, and I'm going to draw this line up. It's going to intersect here. It's going to come up. This is my sigma prime C. Well, then you need that. If you have a really good laboratory curve, you basically don't need Casagrande's method. If you have a crappy laboratory curve, then you need some method to do this. But what's the real problem? The real problem is you don't have a good sample. If you've got a highly disturbed sample, you should just give up on trying to get it returned to the field condition and go out and get a good sample. I skipped Salfer's method, which you can read is slightly different. In Salfer's method, you draw the tangent here. You draw these two lines. You draw the tangent there, and I'm sorry, I'm forgetting exactly what it is, but the procedures are in your book or in your text. And you get the preconsolidation stress down there. But notice that I just did the preconsolidation stress with Casagrande's method, and you're going to get this one. If you actually have to do these things, I guess it's good that you have a standard method to do it, so at least everybody in your lab does it the same way. But the real problem here is you've either got a crappy sample, or if you have a curve that in semi-log space that goes like this and just keeps turning over and turning over, what might that curve look like if you plotted it in arithmetic space? We went through this. It might be pretty straight in arithmetic space. It might be that you're just looking at something that you shouldn't be plotting in semi-log space in the first place. So this is the one I really dislike. So this is Casagrande's and Schmertmann's method for determining the field, the quote virgin field curve from bad lab data. That's my interpretation. If you start off with this is the sample disturbance one. I'm sorry. This is showing you what happens if what the field curve really would look like is if somebody knew, and then this is a sample that's a good sample, and then this sample is a really bad sample. And notice that, let's just do Casagrande's construction real quick on these. So on this one, I think the point of maximum curvature is here. So I'm going to draw my line there, I'm going to draw my tangent here, I'm going to bisect that, and I'm going to extend this thing up here, and I'm going to get this sigma prime there, pretty close to the field one. On this one, I think the point of maximum curvature is right here. I'm going to draw my tangent, I'm going to draw my horizontal, I'm going to bisect them, then I'm going to extend this thing up here, and I'm going to get a sigma prime c that's back here. And realize we're on a semi-log curve, so those could be quite a bit of distance apart. So obviously, if you got that crappy curve, you're probably never really going to get back to the field curve. And this is the one I really dislike, is Schmertmann's method. So do you guys remember reading Yanbu's comments there where he talked about, that he says C sub c is worthless, and on top of everything else, you're determining it from a line that's drawn outside the data that was even. Do you guys remember when you were learning interpolation and extrapolation in middle school or high school? You know? What's the nice thing about interpolation? You can't be too far wrong because you're in places where you have data. And what's bad about extrapolation is you're driving beyond your headlights, right? You're driving faster than your headlights can go. You have no idea what's out there. So what I really dislike about this method is you're extrapolating. You're going outside of the bounds where the data are. And the reason we're doing this is because we have crappy data. So go get good data. If it's important, go get good data. But if you're stuck with bad data, you're stuck with bad data. You can do this reconstruction. I think it's pretty risky. I mean, you do kind of know that you're sort of going in the right direction. You know that the answer can't be below the lab curve, and it's someplace above the lab curve. But you're pushing yourself out beyond where the data are. And I know that for fairly stiff soils, because I've seen my students do this for our undergraduate lab, you get really bad answers if you go out. If you have some, like around here where you got these partially cemented silty sands and stuff, and you go out and do tests on those. If you do Schmertmann's method on those, you're just going to have an answer that doesn't make any sense at all. Because if you plot them in arithmetic space, you find out they're pretty linear. So, my voice is on. Anybody remember Lost in Space? No? Oh well, never mind. I had a cute little thing to play, but I'd have to plug the sound in for you guys to hear it. So this is the Yanbu quote that I really, really like. So Yanbu said that a lot before 1998. I think I discussed this before, that work by Yanbu is actually probably done started 2 decades before that. This is just when he finally printed the paper out. So anyway, I'm a big fan of not using E log P curves. And here's what Holst and Kovacs had to say about it from your text. So this relates back to the very, 2 blocks ago we were talking about stress strain curves. Is when you look at E log P data, before you do a lot with it, make sure that you plot an arithmetic space, get a pretty good idea of what the best way to approach is your settlement calculations, whether it's to use the E log P. There's nothing wrong with using the E log P method if it properly represents what you're planning to do. And don't assume that there's any significance whatsoever to sigma prime P. There may be a physical significance to it, there may not. The only thing you know for sure is that it's the place where these 2 lines intersect. Let's see, let me get back to one of my plots. Go the other way. All you know for sure is it's the point where those 2 lines intersect on a semi-log plot. Now, if that's an appropriate way to deal with the soil that you have, great, do it. And if your soil is strain hardening and it has a typical strain hardening curve of a soft clay or of a sand, then that semi-log curve can represent it pretty well. We've looked at it. I mean, if your data are plotting along this line and you have a good sample and they're plotting along that line, fine, use it. But if you're deriving this thing from a curve that looked like this, I'm not sure that's what you want to be doing. So don't confuse mathematics with the way soil really behaves. So here's my comments on E log P methods. So these parameters, C sub C, C sub R, and sigma prime C, or C sub E alpha, C sub C alpha, or C sub R alpha, these are just fits to the data in semi-log space. That's all you know for sure. Okay? There may or may not be any physical significance to them. So what are my recommendations? I like both comments, both from your textbook authors and from Yanbu. I think you need to be consistent with those. Get high quality lab data and just throw the trashy data away. If you got bad data, you got bad data. You know, we got lots of euphemism for that. Don't make a silk purse out of sow's ear. You know, every language has got the names. If you got garbage, you got garbage, and polishing it up it's still garbage. When you do plot, I would just use the strain plots. Don't mess around with void ratio plots. There's not really any reason to do that, although Dr. Measure is going to turn over in his grave if he ever listens to this. You take the data in the lab in displacement. All you got to do is divide by the original height, and you got strain. That's the way we take it. If you convert it into void ratio, then when you do the calculation, when you got to divide by C sub C over 1 plus E naught, you just have to convert back into strain. So just leave it in strain, and you don't have to mess with it. And do check. We've said this is repeated now. Do look at the plots both in arithmetic space and semi-log space, and then make a conscious decision about which one's the appropriate one for you to use for your problem. If the semi-log space works, use it. But just don't assume that the sigma prime C has any physical significance. And if you want to use the secant modulant method, that's great. Go right ahead. Whichever one's the most appropriate. All right, let's talk a little bit about layered systems and how we do these calculations a little bit. So I place on the, I'm going to do these just as surface loads because it's a little easier. We got a footing, it's got a finite size, I put it on the ground, and I'm going to plot delta sigma z as a function of depth, and you guys did this exercise with your spreadsheets, and that's the plot of delta sigma z as a function of depth under the center of the footing, right? Everybody did that? All right. So I've got a soil. I'm going to divide it up into layers to do my calculation. And in each one of these layers, so if the soil is a finite size layer, delta sigma prime 0 is clearly changing as I go down, right? Because the overburden stress is increasing. So as I go down in depth, sigma prime 0 is changing, right? Delta sigma z is changing as I go down in depth. because of a load distribution, right? Because of elastic load distribution. C sub C and C sub R and E naught all change with depth. In this case, because the soil's changing with depth, right? I got potentially three different soils. I'm gonna have three different properties. So when I do these calculations, I've got to make sure that I break the thing up into layers. Now, what if I have a uniform soil, a soil that I identify as a single geologic soil, so it's all one soil, and I've got an infinitely large stress. I've got an embankment load like you're doing. You're going to find out that the width of your embankment compared to the thickness of the compressible layer in your problem is very big. So you can treat this as a one-dimensional problem. There's no stress distribution, right? If this is, I hope I did this right. If this is delta sigma z, if this is delta sigma z applied here, it's the same all the way down, right? I have the same delta C. If that's a infinitely large load, I got the same delta. So that's the same with depth. If it's the same material, then C sub C and C sub R and the OCR are constant, or sigma prime m if you want to use the preconsolidation margin. Those are all constant with depth. But what changes with depth? Because if I say I have the same soil, I'm saying that my E log P curve for the soil, log sigma prime versus E, or the void rate, I'm saying that I have the same slopes, right? I have the same C sub C and I have the same C sub R. Well, sigma prime 0 is changing with depth, right? It still changes with depth. And whether I have the same overconsolidation ratio or the same overconsolidation margin, whichever way you say it, at different depths down here, I'm on different curves. Just like I showed you before, at each depth, I'm going to be on a different curve, and I'm going to have a different sigma prime C for each curve because I'm starting at a different initial condition. So even if it's the same amount, even if it's the same soil with the same C sub R and the same C sub C and the same overconsolidation ratio, I'm starting at a different point. So the point where we move from the reload curve to the version curve is a different stress. So you got the same lines, but they intersect at different places. So when I'm doing this calculation, even though I have a uniform soil with a uniform change in stress, I still have to break it up into layers to do the calculation correctly because I'm starting at a different point in each sample. So I can't, and the place where I'm going to get most of the compression is still at the top, because if you think about it, that's where the soil has the highest void ratio. It's going to be at the top, and down at the bottom it's got a lower void ratio. And if you think about this curve, remember this curve, if I plot this curve in arithmetic space, remember it's just getting stiffer all the time, right? If this is a plot of strain versus sigma prime, it's just, right, it gets stiff. If this will plot the same as if I have a virgin material and, whoops. Sorry. Log sigma prime versus, right? A straight line here is going to plot like with in arithmetic space is a stress displacement curve that's getting stiffer with, right? So what's happening farther down here is I'm on a stiffer part of the curve. So I'm going to get less strain for the same change in stress. So even when you have a quote uniform material, it's really not a uniform material. We're saying it material has the same stress strain behavior, but you're starting at different places, and so farther down it's a stiffer material. So you got to make sure that when you're doing these calculations, you break them up into layers, even when you have a uniform material. All right. So, process for determining the magnitude of settlement using the E log P method. First of all, you need high quality samples. You should plot you should plot the strain versus log of stress or the void ratio if you want to use that. And you should plot them just in arithmetic space to make sure that you know how it's behaving. And then whichever one of those is the most appropriate curve is the one you should use. You've got to compute delta sigma z as a function of depth if you have a finite size loading. If it's a footing or a mat foundation or something that's relatively small compared to the thickness of the layer that you're dealing with. You have to divide the soil up into layers. Now with spreadsheets and computational methods right now, this is a lot more trivial than it used to be. Because you can go into spreadsheets and once you can figure out how to do your calculations, you can put in 30, 40 layers and it's not a big deal. But if you're doing a hand calculation, you need to use at least 4 layers in any compressible strata. And so you're gonna divide up into layers at those places where the soil properties change, that's pretty obvious, and also places where there's significant changes in delta sigma z. And then if you're using the E log P method, which we're talking about, you're going to use this equation to compute the primary consolidation settlement. Or if you decide to use a modulo space method, then you're just going to go back and use those modulo space methods we talked about before. So if you use the modulo space method, then you can just use this other equation. You're just going to say the settlement's equal to the change in stress of each layer times the modulus. Oops, that's divided by, right? Sorry, there's an error. Yeah, that's right. So you can use either one, but decide which one you're going to use. Okay, so let's talk about where did we get that? Did I go too fast? You good? Okay. What do you do if you don't have any data? Well, what you should do if you don't have any big data is go pay somebody to get some data for you. But if you need to do if you need to do some quick estimates on magnitudes of settlement on the back of the envelope, because you got to figure out if you got a problem. There are a bunch of empirical correlations for different samples. This one is of very little value to you because it's, this one is based on remolded samples, so that doesn't help you very much. Let's see. See, this one's, yeah, this one's based on remolded samples. I believe that's correct. I guess you should look that up and make sure that I said that correctly. And it makes sense that if you got a higher liquid limit, that you should have a more compressible soil, because the higher the liquid limit, the more compressible the soil should be. There's ones based on the water content. There's ones based on void ratio. If you notice, a lot of these are pretty old. The other thing you can use, which is pretty helpful, is if you have local correlations with materials you know. For instance, San Francisco Bay, most people can tell you what the coefficients of compressibility are going to be, and depending on where there's young bay mud and old bay mud, and then there's stuff that's highly organic. And so you should at least have an idea of what's going on there. If you need to do a back to the envelope calculation in San Francisco Bay mud, just take one of these values and run off with it. And you can see there's other ones at other places. I got some from Sao Paulo and some from New York City marsh deposits. So if you have those local kind of correlations, that's great. Get your index properties, do a back of the envelope calculation. And if the settlement's like really, really important and really critical for your project, then you better go get samples and do it. If it turns out, hey, I'm computing 6 inches of settlement for this embankment, I really don't care, because by the time I get this constructed, we're not going to care, then fine, then don't spend your time getting samples. But if you find out it's important or significant, then maybe you need to go do get samples and do your calculations. But it's a good place to start. And here's a whole bunch more here. I just put this here so that you can see that in your textbook he gives you a whole bunch more. The ones I put in the previous slides, I think, are ones that were not in your textbook. So it's an okay place to start. It's a bad place to end. I do like these qualitative descriptions of compressibility. If you want to talk to somebody about what's compressible, and for you, if you have very little experience, you don't know. If somebody says, "Hey, I got a C sub C of 0.1," you're like, "Okay, what is that?" I mean, you know what the modulus of steel is. You might know what the modulus of concrete. What the hell does that mean? Well, this is a nice description. I think Professor Caduto developed this description. I think it's a nice description of the slope of the curve. And so when somebody tells you that they got a C sub C epsilon, that's 0.2, you go, ooh, that's soft stuff. That's very compressible. So this is a nice way for you to calibrate your engineering engineering judgment brain. That's about all it's good for, but it's good for that. Okay, that's that part. Ooh, we're right at break time, so we're gonna take a break.